But it's an honor to have Sasha Efimov from State Club and HSC, and he's going to be talking on the equivalence algebraic varieties.
Yeah, thank you. Thank you very much for the invitation. So yeah, I will disprove two over-optimistic conjectures on equivalence of algebraic varieties. But first, I need to recall what is equivalence, what I mean by equivalence. So for simplicity, all varieties are over complex numbers, so recall the Grothendieck ring of varieties. As an abelian group, it is generated by the isomorphic classes of just reduced separated schemes of finite type, or if you wish, just quasi-projective varieties, but reduced. Subject to relation that x equals z plus the complement for any closed reduced subscheme z inside x. And the product is given just by the product of varieties. Obviously, it's compatible by the compatible with this relation. We denote by L the leftist class, which is just the class of affine line in this ring. And by definition, the varieties x and y are said to be L equivalent if their classes are equal in the localization of this ring with respect to L. So this means just, in other words, it means that the difference in the Grothendieck ring is annihilated by some power of L. So this is the general notion, and of course we will be interested in the case when x and y are smooth projective. It was proved by Luyenge and Bittner that this Grothendieck ring has another description which is very useful for many for constructing some invariants, for example, and which works over any field of characteristic zero because you need resolution of singularities. And as an abelian group, it is generated by the isomorphic classes of smooth projective varieties with the following relations. So first one, very important, is the class of empty set equals 0. You cannot avoid this for some stupid reasons. Another relation is that when you have some smooth projective variety and you have a closed smooth subvariety, Z is closed, of course, and you take a blow up and you have exceptional divisor, then you have this relation that x plus z equals y plus e. And obviously these relations are satisfied for the usual definition of the Grothendieck ring of varieties, because x minus z is just the class of the complement, and this complement is the same as y minus e, so it is the same as class of y minus class of e. So you see that this relation is satisfied. And to prove that these two relations are sufficient so that you indeed get a description of the same Grothendieck group, you need to apply Wick factorization theorem. Well, first you can cut any variety can be cut into smooth pieces just by some stratification, and then you can use smooth compactifications. That's why at this point you already need characteristic zero, and then you apply Wick factorization, and you can show that these two relations are sufficient. Okay, there are a lot of interesting examples of L-equivalent varieties. Well, mainly case-3 surfaces, but also some other examples. And I will not recall them because it will take some time. But I'll just say that constructing such examples is an interesting and challenging task in various contexts. The following general conjectures have been made in the papers by Huybrechts and also by Kuznetsov and Schindler. So first, a conjecture by Huybrechts about isogenous case-3 surfaces. That he conjectured that if S and S prime are complex projective case-3, then having an isomorphism of rational Hodge structures is the same as having isomorphism of rational Joule motifs, and that it is the same as equality of S and S prime in this localized Grothendieck ring of varieties. Well, it's
reformulation of all conjectures of closures.
which old conjectures?
So we get this paper on equilomorphisms.
No, I don't think that the third statement is a reformulation of something. The third is some naive guess which was disproved.
So there are people who are thinking that they should be called Kalmar.
Counterexamples to what exactly? To
both.
I see. Yeah. Yeah, but he also added some that probably you need some appropriate localization, but as it will be shown, no reasonable localization can save the situation. So what is not invertible? The class of affine line? It is obviously non-invertible. Yeah. But what's the question? What do you mean? I mean, just if you have commutative ring and you have an element, you take localization. What's the problem? Yeah. Okay. So this is the first conjecture which I'm interested in, and another conjecture by Kuznetsov and Schindler that if X and Y are smooth projective varieties which are derived equivalent, then they conjecture that these varieties are L equivalent. And we will disprove both of these conjectures, and it's funny that they were modified in the published versions of the papers after I've disproved them. So it's like some kind of Escherian situation, like in the picture of Escher. Well, namely, Huybrechts just simply removed the third statement from the paper, and Sasha and Zhenya, they just added assumption that X and Y to be simply connected. But I think this new conjecture also fails. It's like Platon was defining what is a human, and Diogen was just brought him the chicken, which satisfied all the conditions. And I think Platon. Give the definition. Okay. Yeah. But in this talk, I'll explain why both this conjecture fail in the original formulation, and also we'll prove some interesting results that both for abelian varieties and for K3 surfaces, in each L equivalence class, you have only finitely many of varieties. So it's some. Like, for example, as you know, there are only finitely many Fourier-Mukai partners in each of these cases, and also it turns out that there are also finitely many L-equivalent non-isomorphic varieties in both of these situations. And our tool to distinguish L-equivalence classes will be the Hodge realization, and all results on non-L-equivalence will be deduced from the very general, and I was really surprised that these are new results on the Grothendieck group of an additive category under the assumption that the morphisms are finitely generated abelian groups. So first, I just recall that it's just a notation that HS sub Zn will be the category of pure polarizable integral Hodge structures of weight n. These are just finitely generated abelian groups V equipped with the decomposition that V tensor C is decomposed into the direct sum of VPQ, such that VPQ bar just complex conjugate equals VQP. And also you need a polarization, standard notion. Also we can take just formally the direct sum of these categories. It's a standard operation on additive categories. So HS sub Z denotes the category of graded pure integral Hodge structures. And by K0 additive of HSZ, we denote the Grothendieck group of this additive category. And I'm putting superscript add here to stress that we ignore the fact that these Hodge structures form abelian categories. So we don't take into account short exact sequences. We just taking K0 only up to direct sums. That is, if we have any additive category, category B, then I'm taking, so K0 is generated by just isomorphism classes of objects and relations, and the relation is that the class of V plus W equals class V of class plus just the usual plus the class of W. So no short exact sequences are involved here because I mean for natural additive category we don't have any natural exact structure, just the trivial one. And yeah, so this is K0 of Hodge structures. And obviously we have a direct sum decomposition, so this K0 splits into the direct sum of Grothendieck groups of Hodge structures of weight n. Yeah, and we actually have a well-defined homomorphism of abelian groups from K0 of varieties to K0 of Hodge structures, and it is given by Hodge applied to X is just the cohomology of X for X smooth projective. And know that I don't need to take alternate sums here because it's not about abelian categories or triangulated categories. It's just K0 of an additive category. That's why I just don't need this alternate sum here. Well, I could take I could do it, but it's not necessary. So it's just the sum of this class of cohomology of X is just the sum of classes of HI of X over I from 0 to dimension of X. No, that's the point. That I mean. Yeah, but I know that I'm taking only smooth projective, so it's not. I mean, in this setup, I cannot immediately define the value of this functional for non-compact and singular varieties, because of course I can take mixed Hodge structures, but it doesn't work. So it's like. Yeah, I'm just saying how I defined it. So for smooth projective X, I defined it like this, and then I only need to check the relations, and perhaps you can believe that it holds for the empty set and for the situation with the blow up. So suppose that again, as above, we have this. Z inside Y is a smooth variety, and we're taking blow up, and E is exceptional divisor. Then we have decomposition of the integral Hodge structures. So cohomology of E is actually just a projective bundle over Z, so it decomposes into a cohomology of Z plus cohomology of Z twisted by -1, T twist, and so on. Cohomology of Z twisted by 1 minus C. And but also cohomology of X of the blow up is also the direct sum. Cohomology of Y plus twists of cohomology of Z. And so, in particular, we see that we have just an isomorphism of Hodge structures between cohomology of X plus cohomology of Z and cohomology of Y plus cohomology of E. And in particular, we have an equality in the abelian group, an equality of elements in K0 additive of Hodge structures. And this means that the relation satisfies. Yeah, and for non-projective and singular varieties, it's not so straightforward to give the value of this functional. Yeah. Okay. Yeah, and but we are interested in the. So this was the functional from the Grothendieck ring of varieties, but yeah, and know that it is only a homomorphism of abelian groups. It's not compatible in a nice way with the ring structure because of torsion in cohomology. But we are interested in the localization with respect to the affine line, and let us know that if we multiply the class of x by L, then this functional indeed we obtain the Tate twist by -1. It's because if x is smooth projective, that then L times x is just the difference between P1 cross x and x. And of course, we know that cohomology of P1 cross x is cohomology of x plus twisted cohomology of x. So this equality holds, and because Tate twist is of course an autoequivalence of integral Hodge structures, so we have a well-defined homomorphism from the localization to the K0 additive of Hodge structures, which is given by this formula, so in the obvious way. And we will use this invariant to distinguish the L equivalence classes, somehow it disappeared from the slides, and all our results on non-L equivalence will be deduced from the very general results on additive categories. So we will apply these general results to the category of Hodge structures. So now let's consider the abstract situation. Let A be some abstract small additive category such that all the morphisms are finitely generated abelian groups. For example, of course, this holds for A equals to HS over Z. So our first general result, which is really surprisingly new, that if we have two objects in such a category which are stably isomorphic, which means that their classes are equal in K0, and endomorphism of one of them is integers, then these objects are actually isomorphic. About this result, I mean, for me it was, when I realized that it should be true, it was really fast for me to prove it. But everyone, so I asked a lot of people about can they prove this immediately, and everyone failed, and they asked me how this can be proved, and including Bailenson, for example. So it turns out that well, yeah. No, I don't assume. Anyway, you can embed it. You can take Karoubi completion, and the homomorphism is injective from K0 of A to K0 of Karoubi completion. This result actually holds if you assume that endomorphism of V is contained in some more general class of rings. So we can make some weaker assumptions. For example, matrix algebra over Z also works. But for simplicity, and the proof is really simple in this case, and for the applications, I need this situation. So we restrict to this special case. And I just recall that equality of classes in K0 of A means that there is some object U in A such that the direct sums are isomorphic. So this means that V and W are stably isomorphic. To prove the result, we need a useful but quite standard notion of a Krug-Schmidt category. So recall that a small additive category B is called Krug-Schmidt if for any object we have decomposition V into the direct sum of some VI's such that all the rings for each of these VI's, endomorphism of VI is a local ring. And in particular, for any field, if you take Karoubi complete K-linear category with finite dimensional morphic spaces, then this category is Krug-Schmidt. And probably I should just recall, it's very easy that it follows from the standard fact that if A is finite dimensional K algebra, so finite dimensional algebra over a field, then we have two situations. Either there exists some non-trivial idempotent, so there's some E in A such that E equals E squared, but E is not 0 and not 1. Or A is local. A is a local ring. So we have only two situations, and so as long as you have such idempotent, you can split your object into. If A is any associative algebra with unit, then it's local if it has some. If it has two-sided ideal such that the complement of M is contained. Actually, it's the same as it coincides with a set of invertible elements. It's there are different characterizations of the same story. Yeah. Yeah. So if you are in the K-linear situation of a field and everything is fine dimensional, then you only need Karoubi completeness. I mean, so that you can take the image of every idempotent, and then this category will be Karoubi-Schmidt automatically. Yeah, and the following is a standard that in a Karoubi-Schmidt category, any object has essentially unique decomposition into a direct sum of indecomposables. This means that if you have two such decompositions, then these collections of summands are isomorphic. So you have a bijection between summands, so that the corresponding summands are isomorphic. And in particular, in such a category, a stable isomorphism implies just an isomorphism. And in fact, this K0 is a free abelian group generated by indecomposable objects. Let's use the following notation that for an additive category, we denote by B bar its Karoubi envelope, and also for an associative unital ring, we denote by B sub R the tensor product of B and R. Or, well, tensor product is by default over integers. And it has the same objects as B, and the morphisms are given by B by the morphism by tensoring the morphisms in B with R. And the composition, of course, comes from the composition in B and the product in R. And from this above discussion, it follows that for any prime number P, yeah, and A is satisfies the assumptions. So A in what follows, A has this assumption that the morphisms are finitely changed abelian groups. In particular, we see that the Karoubi envelope of A tensor Fp is Karoubi-Schmidt. So now we can prove the theorem. So, and it's really elementary. So first, for a prime P, we have this projection functor to this extension of scalars, so by assumption we have this equality in K0 phase. Then of course we have an equality in K0 of this extension of scalars of this A mod P, and so we have an isomorphism between V mod P and W mod P. Because endomorphisms of V are Z by our assumptions, we have that for any pair of these objects, the morphism after tensoring with Fp, the morphisms are just Fp. So because if you have two isomorphic objects and endomorphism of one of them is Fp, then morphism between any two of them is just Fp. Now, if you have some finitely generated abelian group, and you know that A tensor some group A, and if you know that A tensor Fp is Fp, then of course A is just integers. And in particular, we have that morphisms between any of these two objects is Z. And now you can take just generated morphisms. So the morphisms form a cyclic group. If we can take F from V to W to be generator of this cyclic group, and G similarly for G from W to V. And then you know that F mod P and G mod P are isomorphisms between this V mod P and W mod P. And it follows that Fg is not divisible by P for any prime P. Which of course means that if you have an integer which is not divisible by any prime number, then it is plus minus 1. So Fg is plus minus identity of W. And similarly, Gf is plus minus identity of V. And this means that V and W are isomorphic. So it's a very general result. It's really an elementary proof, but somehow it's. I didn't meet any other person for whom it's immediately obvious that it holds. Yeah, and now immediate implication that of this general statement that Kuznetsov and Schindler conjecture fails. So if we have some abelian variety which is simple, so whose endomorphisms are just integers, of course this holds for a generic abelian variety. Then first, for any other abelian variety prime such that Hodge structures on H1 have the same classes in the Grothendieck group, we have in fact that A is isomorphic to A prime. And then for any abelian variety which is L equivalent to A, we have that it should be actually isomorphic to A. And in particular, we can take A to be, if we assume in addition that it is not principally polarizable, then it means that it is not isomorphic to a dual, but and we already know that it's not L equivalent to a dual, but still, of course, we have a classical derived equivalence given by Poincaré line bundle between A and a dual, and so we see that the derived equivalence doesn't apply L equivalence. Yeah, and this follows from the general statement just by noting that you can, of course, reconstruct abelian variety from its Hodge structure on first homology, and this functor is contravariant fully faithful. Yeah. So this is the first general statement and its immediate application. And now the next statement it's more tricky. Yeah. So it states that with the same assumptions on A for any object V, there are only finitely many isomorphism classes of W such that V and W have the same class in the Grothendieck group. So it's finiteness result, and this is yeah, the proof is less trivial, and the crucial point here is the following lemma, which is proved very similarly. Suppose that V and W are two objects which are stably isomorphic in A. Then V is actually a retract of W to the power n for some n greater than 0. Well, retraction means it's a standard notion. It means that we have some morphism from V to W to the power n, and then back, so that the composition is identity, is a notion which makes sense in any category. Yeah, and moreover, this n can be taken to be this maximal over all prime numbers of the dimensions of endomorphisms of W tensor Fp. This number, I mean, if you replace endomorphisms of W by any abelian group, this is just the smallest number of generators of the abelian group. So this is there's effective bound on this n, and this is proved in essentially the same way as the theorem about stable isomorphism when endomorphisms of one of the object integer numbers. So it is the same idea to reduce to Kroll-Schmidt categories by taking our category mod P, and we just show that the two-sided ideal generated by the compositions is the unit ideal. This is exactly what we need, because if you know that this is a unit ideal, then you represent the identity morphism as a sum of compositions, which exactly gives such a retraction. And then then the proof is essentially the same. So if this quotient by this ideal would be non-zero, then some prime number acts non-trivially on this quotient, and then you're getting a contradiction by taking a mod P for this prime number. So it's essentially the same idea, but it's a very strong statement for this this Grothendieck group of this category. And another important ingredient and is very old theorem, but for some reason it's not widely known. Theorem of Giordano and Westinghouse, that if you have a fine-dimensional semi-simple algebra over rationals, and we have some order. Well, order is just Z lattice, which is a subring. Then for any positive integer, there are only finitely many R models which as a Abelian group are torsion-free and finitely generated of rank n. And using this, we show that for any you can show that for any ring which is a finitely generated Z model, and for any positive integer, there are only finitely many isomorphic classes of n-generated projective right R models. This essentially reduces to Giordano's house by taking essentially the quotient by the radical. So you can take R tensor Q. You have you have a radical here, radical ideal, just by Jacobson, and then you can intersect it with R, and everything reduces to the quotient of R by J. And this is because when you have nilpotent extensions, then this isomorphic classes of projective models, so you have bijection with respect to extension of scalars. So essentially this statement reduces to Giordano's house. And then using the above lemma, so if you know that stable isomorphism implies that each of these objects is a retract of direct sum of copies of another object, we can replace A by the category of projective models over the endomorphism ring, and then we obtain this finiteness result. Yeah, and immediate application of this is that there are only finitely many abelian varieties in each stable isomorphism class, and in particular also in each L equivalence class. Well, here by stable isomorphism I mean that abelian varieties by themselves they form an additive category. So we have a notion of stable isomorphism, and this essentially is a straightforward application of the general finiteness theorem for additive categories just by using Hodge realization. And in fact, there are no known examples of abelian varieties which are L equivalent but not isomorphic. And it is not clear whether stably isomorphic abelian varieties are L equivalent. And at least in the example of Schroeder of two elliptic curves, so Schroeder there's an also old paper of Schroeder where he constructs two elliptic curves E and E prime. Well, of course, there was complex multiplication. Otherwise, this is impossible, such that E is not isomorphic to E prime, and there exists some other elliptic curve E double prime, such that the products are isomorphic. So, in particular, these two elliptic curves are stably isomorphic, and there's no abstraction for. There's no, clear abstraction for them to be equivalent, and it would be interesting to know if they are or not. Yeah, and to apply our general result to case-3 surfaces, first need the following proposition that if you have a case-3 surface S, then there are only finitely many non-isomorphic case-3 surfaces S prime, such that the Hodge structures on H2 are isomorphic, but we don't require isometry, because if you require isometry, then by global Tarrelli theorem, you know that S is isomorphic to S prime. But here, we don't need don't assume compatibility with the intersection form. Yeah, and then there's this finiteness statement, which is not hard actually to prove. You can, well, but it's some technical considerations. You reduce to consideration of possible Hodge pairings on the transcendental Hodge substructure, and you use Zarhin's theorem on the endomorphous field of the rational Hodge structure of transcendental cycles, which is either a totally real number field or a complex multiplication number field, which is an imaginary quadratic extension of totally real. Yeah, there's some technical proof, which is some playing with linear algebra. Yeah, and then if you know this finiteness statement, then we deduce that each L-equivalence class of K3 surfaces contains only finitely many isomorphous classes. And this follows just by the Hodge realization from this proposition about finiteness and the finiteness theorem for additive categories. So this is just again straightforward application. In particular, Huber's conjecture fails. So this implication that first implies third, it fails already for Kummer surfaces because of course there are countably many Kummer surfaces in each isogeny class. This is because isogenous abelian surfaces give you the same, give you isogenous Kummer surfaces, but there are only for each Kummer surface there are only finitely many possibilities for abelian surfaces which give it by the Kummer construction. So of course, if you have a countable set, and we assume that, and we already know that each L-equivalence class is finite, then of course there are some isogenous surfaces, isogenous Kummer surfaces which are not L-equivalent. And we have more precise, we can make a more precise statement. So this isogeny for K3 surfaces, it is weaker than twisted derived equivalence. So recall that a twisted K3 surface is a pair S and alpha, where alpha is it's not Brouwer of X, it's Brouwer of S. Where alpha is an element of the Brouwer group of this surface. And so we have an abelian category of, again it's S here, abelian category of twisted coherent shifts, which are shifts of models over the Asimov algebra. And we have the twisted derived category. And we have the following corollaries that there are actually twisted K3 surfaces S1, alpha1, and S2, alpha2, which are derived equivalent, but the underlying K3 surfaces are not equivalent. And this actually follows from the previous statement, because it was proved by Hubricht that for isogenous K3 surfaces, there is a chain of K3 surfaces S0, S1, etc., Sn, which starts from S and finishes by S prime, such that for any consecutive pair for any pair Si and Si plus 1, we can find some Brouwer classes so that we have this twisted derived equivalence. So if we already know that S and S prime are not equivalent, then some Si and Si plus 1 will be example which is stated in this corollary. Yeah, so and we can actually make this more precise. So there's a huge class of this example of such situation. So first, an application of our first theorem that so the statement is that if S and S prime are L-equivalent K3 surfaces, if we assume that endomorphism of the transcendental Hodge structure for S is just Z, which again happens for generic S, then we have an isomorphism of Hodge structures T of S and T of S prime. And it is almost the same as derived equivalence between S and S prime, because by Orlov's theorem, you only need Hodge isometry between T of S and T of S prime. So it's very closely related. I mean, to apply this general theorem on additive categories, it's sufficient to know that there is a well-defined additive functor and the functor of Hodge structures, which assigns to each Hodge structure its transcendental Hodge substructure. This is well-defined for any polarizable pure Hodge structure, which is a standard thing. Yeah, and general class of examples is that you can take any K3 surface whose Picard number is at least 12, and which is generic, which means that endomorphisms of transcendental cycles is just integers, Hodge isomorphism or Hodge endomorphism. And if we take any non-trivial Brouwer class, then there is a K3 surface S prime, such that dB of S prime is equivalent to dB of of S twisted by alpha, but S and S prime are not L equivalent. This existence of such S prime with this equivalence was proved by Hubrechts, and in fact, just by construction, if I identify the Brouwer group of S with homes from transcendental lattice to Q mod Z, then we have an isomorphism of Hodge structures between T of S prime and the kernel of this map from T of S to Q mod Z. But on the other hand, if S and S prime are equivalent, then we already know that the transcendental Hodge structures are isomorphic by the above propositions. But then it's just a statement about abelian groups that this is impossible because T of S has rank at least 2 over Z. So such situation is impossible if alpha is non-trivial class. Yeah, and finally, I just mention some remarks. So that yeah, as I already mentioned, Kuznetsov and Schindler have modified their conjecture by assuming that varieties are simply connected, and I'm actually sure that it still fails, and you can. If you try a little bit, I think you can disprove it again on the level of Hodge realization. However, it seems that for K3 surfaces, the conjecture holds, and moreover, D equivalence is probably just the same as L equivalence. So probably it also holds in another direction in this situation. Yeah, and challenge here is proof or disproof existence of L equivalent, but not isomorphic abelian varieties. So I don't know any reason, any obstructions to non-L equivalence in this situation. So I think I'm done.
Any questions? Well, thank you very much.
Thanks.